So standing waves, as we mentioned earlier, they are the result of an interference pattern. Caused by two waves traveling in the opposite direction.
Yes.
And this is usually, the same wave reflected. That's the most common situation we see.
Yeah.
Because if it's the same wave reflected, that means it's got the same velocity and frequency and wavelength, which is therefore allows you to get your standing wave. And as we mentioned, because you need reflection, this is usually in an enclosed space. So e.g. in a room or a medium. So for example, in a fixed length of rope or string.
Yeah.
And you'll see that coming up very shortly. We're going to be looking at standing waves of strings and pipes, but it can also happen, but basically it needs to be an enclosed space of some sort. And yeah, and then basically the waves will interfere and give you a standing wave pattern where the wave looks like it sort of stays in place. And you can look at what we did last week to kind of get an idea of that. But basically that also means then we say you've got your nodes, which is, displacement equals 0 all the time.
Yeah.
It doesn't move there. The particle doesn't basically move. Basically, it's always destructive interference there. And you've got your antinodes, which is like the maximum displacement. All right. So when you form standing waves, and this is the part that will be new for you, then note that not the standing waves, won't form in all situations. They will form with a particular frequency.
Yeah.
So we're going to be considering different situations. We're going to be considering standing waves in a string. We'll be considering standing waves in an open pipe. And we will be considering standing waves in a closed pipe situation. And we'll examine strings first. So if you have a string, the string is of fixed length and it's got sort of like, point A and point B, right?
Yeah.
Now, if you have a string and it's fixed at A and B, can it move at those points? Can it move at
yes.
A? Can it move at B? Oh, really? How can it move at A?
Oh, no. You mean, okay.
Like it's fixed, right? That's the idea. It's not allowed to move. So if it's not allowed to move, can I get, can a wave have it sometimes going up and sometimes going down? Can that happen? Well, no, it can't, because it's fixed, right? Which means, because it's fixed, as if there is a standing wave, this has to be what sort of thing? If it can't move.
It should move. It should move.
It can't move, so it has to be a node. So what that means is, if you've got the length L and you fix the string here and fix the string here, what that then means is that the standing wave must have nodes at the ends. And this here is what's called the fundamental mode of vibration. And this fundamental mode of vibration here is also known as the first harmonic. And basically, the reason is because that as these points are fixed, that means they must be nodes. The string can't move. And so when a standing wave is formed, it has to, be this sort of shape to start with. And this is called the fundamental mode of vibration, and otherwise called the first harmonic. Remember, that's because these are nodes, and so the string can't move there. Now, having said that, if I take the same string AB, and I set these as nodes, which they do have to be for a standing wave, this wave here like this is certainly a standing wave I could draw, but it's also not the only possible standing wave I could draw with only these as nodes. I mean, if this is a node and that's a node, it could do this and this. And as we said before, think about it. That means this here, the distance between nodes, is half a wavelength. Because, if you think about it, the wave would have needed to continue to get one wavelength, right? And so we would associate this lambda 1 to actually be 2 times the length of the L, and the frequency using V equals F lambda, right? Using the wave equation formula. That means the frequency F1 would be V over lambda 1, which would just be V over 2L. And those are things that you should be clear about for the first harmonic. Now, the fact that we talked about first harmonic suggests there might be multiple more harmonics, and that is, well, true. Because I could have a node in the middle. I could have a wave that looks like this. Now that means A and B are still nodes. Now this is called your second harmonic. And this lambda 2, you can probably see, is just going to equal L, because you can kind of see that this is just lambda. And using the same sort of ideas as before, that means F2 must equal V over lambda 2, which is V over, I guess, L. And if you like, more importantly, you can probably see that it's equal to 2 times F1. So the second harmonic, you can see, is going to be double. The frequency of the second harmonic is going to be double the frequency of the first harmonic. Now, we're going to extend this concept a bit more, and I'll just draw it a few times. So imagine all of these are length L, and all of them are fixed on the ends. Because they're all fixed on the ends, those must be nodes. And as we mentioned earlier, your most basic situation is this standing wave. Okay. That is, repeat, the fundamental mode of vibration, otherwise called the first harmonic. From the diagram, it's probably clear that lambda 1 equals 2L. Okay. This is L, and that's half a wavelength here. And therefore, F1 equals V over 2L. Now this here is called the second harmonic, when we've got a node here in the middle as well, right? So these are nodes, which means that our wave would now look like this. That node is meant to be in the middle. And from the calculations before, we'll notice that lambda here must equal L, and F1 must equal V over L, which equals 2 times F1, importantly. And as you can imagine, this can continue. We can split it into 3, and so we'll end up with something that looks like this. With, of course, nodes here as well. So that's going to be the third harmonic. And that would then mean, of course, that lambda, if you think about it, lambda is this section here now. And if you split the string into 3 equal parts, of which lambda is 2 of those parts, so lambda must equal 2/3 L. And we'll call this lambda 3 and lambda 2 to make up for the fact that, you know, that's what they are. And then, of course, that should be F2, not F. And F3 is going to be, well, as always, V over F, which means it's going to be V over 2/3 L, which you can see is 3 V over 2L, which is 3 times F1. And you can probably start to see this pattern emerge where the frequencies is F1, then F2 is double, F3 is triple, and that will continue as we continue to the fourth harmonic. And you have then 3 nodes in the middle. And you can probably see that this process theoretically can go forever. Now, as far as the fourth harmonic goes, that means your lambda n is, well, in this case, going to be 2 over 4 or half L, right? And your F4 will also be 4 times F1. You can go and derive it, but it will always be that, right? So notice that basically that, you know, I could have a standing wave at this frequency, which is the fundamental. And if I want a higher frequency than that, it has to be this one. I can't have a frequency in between because a different frequency will give me a wavelength which does not have these as nodes. And that's impossible because A and B are fixed. Because they can't move, and because they can't move, if you end up with a wave where it's not a node there, this will just cancel it out. It will stop it happening because you can't move at A and B. So if you've got a string fixed at both ends, which they usually are, then the only way that that can happen is that, you know, you either have this frequency or this frequency or this frequency or this frequency, or basically any multiple of the fundamental frequency is possible. Any whole number multiple of the fundamental frequency is possible, but anything in between is not, okay? Anything in between is not possible. So for a string, we also kind of now introduce other sort of terms, which might be slightly confusing. This is the first harmonic, F1. The second harmonic is sometimes called the first overtone. The third harmonic is sometimes called the second overtone. And the fourth harmonic is sometimes called the third overtone, and so on. And so if we kind of try to put all of this on one sheet with, if we try to generalize this, all right, and let's put it all on the one sheet here. essentially, you could have a string, and B. Now notice that this has 2 nodes. This has 3 nodes. This has 4 nodes. This has 5 nodes. So if we have the nth harmonic, it will be called the n minus 1th overtone, which would have n plus 1 nodes. Yeah, it'll have n plus 1 nodes. And so it will look like, you know, I mean, obviously there's a sort of dot, dot, dot in the middle, right? Think of that as your break line from engineering. And then you'll then have a, ooh, why did I write a? N there, that's a 4. So we'll have lambda n. Now, you'll know that you've split it up into n parts. So therefore, it will be 2 parts out of NL. And your Fn would equal n times F1. And that's what it is in general for a string that is fixed at both ends. So you can have frequencies that are higher than, you can have standing waves on a string. They can have more than one frequency, but any frequency of a standing wave on a string must be a multiple, a whole number multiple of your standing wave. Of course, we're assuming that the string in each case is, you know, under tension and fully stretched and fixed at both ends. Does that make sense? Great. So you'll notice that this depends on the V of the wave. And this V is not talking about the velocity of the wave in air, but it's talking about the velocity of this wave in a string. So the next thing we need to consider is, how do we determine the velocity of a wave in a string?